exciting because it's like working, DX for the first time. So a little background. I am not an engineer, and I don't have technical expertise with these vector network analyzers, let alone the Nano VNA. But I was always interested in antennas, and as I got into adulthood, I studied physics and astronomy. I was mentioning today, but I spent a summer at Royal Greenwich Observatory down in Herstmonceux Castle and lived at Bexhill. So I still have great memories from that summer, both from the astronomy point of view, but even more so from the cultural point of view of, living in a different situation. So the Nano VNA is just a very clever gadget. It's a nice tool. So my approach tonight, or for me it's only 2 in the afternoon, my approach is to sort of give you an overall ballpark of how I learned to use it and what I tend to do with it. Not so much talk about the innards and the electronics and how it works. And questions I often get was, oh, so where should I buy one? I have no idea. The one I have was given to me as a present back in September. And the present had a condition. And the condition was that I learn how to use it and share what I know with my local ham club. So I thought, wait, this is pretty expensive to give it to me as a present. And they said, no, we want you to teach us how to use it. So it took me a month or 2 just playing with it to learn about it, I would say, at about a 3rd grade level. And I gave my first nano talk to our local club. And there were lots of questions, and I realized I don't know much about this thing. I'm just a rookie, too. So it was like a rookie teaching a more rookie. So after, I've given about 15 talks now on the Nano VNA, and each one I'm thinking, well, wait a minute, I remember that question. So I've expanded this thing, so I realize there's 2 levels of this Nano VNA. One is just the fundamentals, just when you open it up and you set it up and you calibrate it, how are you going to use it? But part 2, I've been sort of more involved with lately, and that is, what does this really reveal about antennas or filters or whatever, and how does it work? It's very different from the typical little SWR meter or antenna analyzer you get today. It's a very sophisticated instrument at a very, very reasonable price. So with that, again, I'm going to kind of share what I've learned about this, but because I spent most of my adult life as a high school teacher and the last 10 years teaching pretty young students in 9th grade, like 14-year-olds, I would prefer this were more spontaneous, and if you have a question, press the space bar, unmute, and just really interrupt me and say, so Barry, you're going to cover this? Or I didn't understand that last slide. So don't hold your questions until the very end, because then you'll probably forget. And it feels stale by the end of the talk. So feel free to interrupt, okay? So let me go to screen share, and I'll show you what I've got here. Did that come up? And I'll go to slideshow from beginning. All right. Did that work? David, did that work? Do you see my screen now?
Yeah,
Nano VNA.
Okay, Barry.
Okay, good. All right. So, as I became more comfortable with this gadget, and as I sort of threw together more and more information, more and more slides, I figured there's really 2 parts to this. And part 1 I'll just call the basic stuff without getting too under the hood. And the part 2 is, well, how does the thing really work? What does the phase tell you about an antenna resonance? And what's this Smith chart all about? So part 2 is a little bit more of the in-depth. So I think of each of these, part 1 and part 2, is about an hour. So we're going to just do part 1, the basic stuff here today. So I thought, when I first got this, well, they were about $50 US currency. I remember when I was a kid, I got this Swiss Army knife as I was a Boy Scout, 13, 12-year-old. And I thought, wow, what a nice present, a Swiss Army knife. And I took it camping, and it had all these different blades. You could do all these different things, but mostly I used the one sharp knife and the can opener. It had all these other tools, but I realized I didn't know what to do with them anyway. I didn't need a corkscrew as a 12-year-old. But I loved having it. Just having it just made me feel good that I had this Swiss Army knife. The Nano VNA is a little like that, isn't it? It can do lots and lots of things, but you might end up buying one and just measuring SWR, which you could do with another kind of simple gadget. So I think of this as kind of the Swiss Army knife. Then I kept thinking, what are other analogies? And this popped into my mind, and it's really a better analogy. A stethoscope. Well, we have actually a couple stethoscopes in our house, and it's fun. We have some grandkids now, and it's fun for the grandkids to listen to our hearts, but they have much more fun listening to our tummies, grumbling. Much more interesting sounds. What can you tell about the health of your heart if you're listening to your heartbeat? Well, I can't tell much. I'm not a trained cardiologist, but it's fun to do it anyway. It's actually more fun to listen to your stomach growling. So, a Nano VNA is sort of like, what can you tell about your antenna or your filters? Just like the stethoscope. I thought, well, when I first started to play with the Nano VNA, it produces all of these graphs, and they can be a little intimidating. So I thought, let's take this one step farther. I'm at the age now where I've had a couple of EKGs, or ECGs, electrocardiogram. And, you get strapped in and zip, zip, zip. Technician gets your EKG. In the old days, it got ripped off as a piece of paper. Now it's just, on the computer monitor. But I loved it when it was paper because the technician would rip it off, put it on the doctor's desk. And while I'm waiting before the doc comes in, I pick it up and I start, and I can read a little bit about EKGs, and I see the QRS and the T wave and a little bit this and a little bit of that. So my cardiologist comes in, and he knows I'm a retired, physics prof and teacher, so I say to him, how about if I try to read my own EKG? He looks at me and says, go for it, Barry. So I spent about 1 minute. I look at the amplitude of this and the this and the this. I said, so how did I do? My heart looks actually pretty good from my own EKG. He looks at me, he says, not bad for a third grader, maybe a sixth grader. I said, well, that's a compliment. Tell me what I'm missing. He said, Barry, you're looking at the amplitudes, right? Yeah. He said, look at the phase. I thought, oh. And as I got this Nano VNA, it's the same thing. Look at phase. What does the phase tell you on filters and antennas and all this? Because the Nano VNA can tell us phase. A lot of these other simple meters don't measure phase. Okay, so let's start out with something like this. And I have no idea who the audience is here. So I set my Nano VNA up, and I actually use something called VNA Saver, Windows 10 software. Connects to the Nano VNA. And instead of reading all the graphs on my little screen, I can print them out on my big monitor. So I set my Nano VNA to Smith chart. Now, I'm not going to tell you what a Smith chart is. I'm not going to tell you a thing about this drawing, this graph, but this is my 80-meter dipole. It's an inverted V. And if you just look at this, I set markers 1, 2, 3, 4, 5, 6 every 100 kilohertz. So marker 1, let's see, down here, 3.5 megahertz, 3,500 kilohertz. Marker 2, marker 3, marker 4, marker 5, marker 6. So, I don't know. Can anyone read this like you'd read an EKG? Could you please unmute or press the space bar and say, oh yeah, I see this antenna is resonant at blah. Or it looks like this antenna is going to have the lowest SWR at blah. Anyone willing to unmute and just give me a quick reaction here? What's the Smith chart? This is my 80-meter antenna out in my backyard.
Yeah, go on, Barry. I'll say 3.7.
What? That's marker 3. Then here's marker 3. What about it?
I think that's the lowest SWR point.
And how do you reach that conclusion?
Because it's closest to that particular part on the Smith chart on the bottom line.
Okay. Anyone else?
I could be wrong.
Adam, you're laughing?
Barry? After doing the meeting, can you please put the headphones for charging in my room?
Yeah.
All right, looks like a couple people
It's
are
next to the
unmuted.
bathroom or
So be sure you're muted unless you want to be unmuted. So I don't want to say if that last answer is correct or not, other than this is sort of like me reading my EKG. Maybe I have a little knowledge, maybe don't quite get it right, but this is one of the things that you can easily get in, under 1 minute with your Nano VNA. This is my antenna. What if I showed you this graph? This is the same antenna, but I set my Nano VNA to read phase. I'm not going to tell you what phase means. But over here on the left, the phase vertical axis here is degrees. Here's 0 degrees. There's 0 degrees. And the horizontal is frequency from 3,400 kilohertz to 4 megahertz, 4,000 kilohertz. Here's the same markers, 3.5 megahertz, 3.6, 3.7, 3.8, 3.9, top of the band. So this is my 80-meter antenna. Of course, I'm measuring this inside my shack, and that's about 150 feet away from the antenna. So could someone unmute and let me know, without me explaining what it is, could you interpret this phase graph of my 80-meter antenna? Unmute, give it a go. How many people do we have in the Zoom now? Over 20?
24.
All right, there's 24 of you. Don't be shy. Or just unmute and say, Barry, I have no idea. All right, silent. See, my 9th graders would never be silent. They'd always yell at me or say something. All right, so do I take it that you're not sure? What's a phase graph telling you? The fact that I'm getting this with a Nano VNA doesn't matter. I just tell you, I get a phase graph. This is what I'm looking at the end of my feed line in my shack. All right, so that tells me something. So let's look at this as just another tool in your toolbox. Now, granted, it doesn't look like, the wrench and the hammer and the pliers and stuff, but let's just treat this for the next hour as just a tool. Let's learn how to use a tool, okay? I'm not going to open it up and show you all the wizard parts inside. Part 2, I'll just say, I've given this talk to some groups, and they said, please come back and do the second part. Now we want to know the details. So I've done that a couple of times. So part 2 is really, what does a calibration plane mean? I'm down here in my shack. I want to know what's going on at the antenna. How do I convert my measurements in the shack to measurements as if I had climbed my tower up there without actually climbing it? What's a complex impedance anyway, and how does a Smith chart record that? What are all these terms I never heard before as a ham? Reflection coefficient. I have never heard that term as a ham. Return loss? Engineers use that. Hams don't use that. SWR, well, that I'm a little more comfortable with. Phase, 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 phase. Come on, Barry, what's phase? My doctor had to convince me to learn about the phase of my EKG. Resonance and lowest SWR. They are not the same. Hams often confuse those two terms. They're two very different meanings. And how do you cancel the reactance if my antenna won't work and I want to be in the shack here and I turn some dials? How do I make the antenna work better? So that's part 2. So let's go back to part 1. What is this thing called a Nano VNA? I thought, here's a better analogy. Bats. Now, I lived and worked at a Quaker co-ed boarding school for over 40 years. We had a lake house, we had bats. Those bats came out at night. What are they doing? They're hunting. They're eating all the insects at night. But they don't see the insects. They hear the insects. The bat emits a pulse of sound. Now, this isn't radio waves. The bat emits a pulse and waits for an echo and has very good ears and hears the echo and can locate the insects flying by how the sound bounces off the insects. Now, if I go yo to an insect, the sound's not going to bounce off at that wavelength. So the bats have to use a really, really small sound wavelength. Again, sound, not RF. So the bats chirp at like 80 kilohertz, and humans don't hear that high. So I imagine bats got very good at finding food and eating it, and the bats that fed better probably reproduced more. So bats have evolved to have very good high-frequency hearing, and they use it to locate their food. Well, so do dolphins. A little different underwater. Sound carries, much faster underwater. But dolphins can locate all kinds of things underwater, including their food and other dolphins, and all sorts of things. Submarines. If you watch the old war movies where the sub goes bing, bing, and waits for an echo, and from the echo they can determine, what else is out there, maybe another submarine. So here we can kind of see and visualize what's going on. The echo tells the bat something, the dolphin something, the submarine something. So does the VNA, except it's not using sound. What's it using? An RF wave. So think of the VNA similar to the way we visualize sonar. So here's just the VNA drawn as a box here. It sends a wave out over a cable. You supply the cable, and that cable goes to some kind of antenna. So I'll look at this from the example of antennas. What would be the perfect antenna? The perfect antenna. Well, if your radio says it wants 50 ohm output, that's what the manufacturer says, you use 50 ohm cable, you connect it to an antenna that says, hey, it's 50 ohms. Perfect. What comes back from the antenna back to the Nano VNA? Absolutely nothing. So it's like the bat or the dolphin goes ping and nothing comes back. Well, that's good for an antenna, right? You don't want any energy to come back. You want it all to radiate. So what if you ping your antenna, like I just showed you my 80-meter dipole, and something does come back? From what comes back, the magnitude, the size of the voltage, and the time delay, I know everything about that antenna at that frequency. Everything. Oh man, that's like the bat is doing well, right? This Nano VNA can tell me the size of the voltage coming back and the phase of the voltage back coming compared to the forward. Phase, phase, phase. What's phase going to tell us? It's going to tell us whether there's reactance in the antenna and how to correct it if there is. So that's pretty clever for, $50 American. So this is as much as I'm going to show you about what's inside the gadget, and I almost deleted this slide. So inside the Nano VNA, there's a little transmitter. Let's call it a source. It only emits like a milliwatt or a tenth of a milliwatt. That signal goes out on a cable you supply to I love this, only an engineer would do this, a device under test, a DUT. So a DUT, when I thought of that, I thought, oh, come on. All right, so it's a device under test. Now, if it's an antenna, there's no through energy, right? The antenna is supposed to radiate it all. But the antenna can reflect some of the energy coming on the cable and just send it right back on the cable. The Nano VNA can measure that returning signal. If it's more like a filter or a bandpass filter or a duplexer or something else, there may be a through signal, like from transmitter through to an antenna. And I'll show you some of those. So if you measure what comes through the filter, compared to what's going into the filter, you get a ratio. And it's the same thing, except we call that the through measured signal. Now, inside the device, there's the generator, there's some comparators, there's, a frequency counter, there's a display, there's a lot of stuff in here, and a couple of batteries. So just look at it from the point of view of the bat and the dolphins. It's sending out an electrical signal, and watch what's coming back. Now, the most common question I heard giving this to a couple of local clubs, and they said, well, how's that different from a spectrum analyzer? They're two very different instruments, but they both kind of look the same on the outside, and they're both very, very expensive. So the network analyzers, the VNAs, they send out a signal and watch what comes back, more like the bat. A spectrum analyzer is just a receiver. It doesn't transmit anything. But what it does is look at the received signal and dissect it in very, very clever ways to figure out more about the waves. And it might demodulate it, so you might catch an AM or FM or PM signal. Yeah, they're both kind of expensive. They're kind of intimidating with lots of dials and stuff, but they serve two different purposes. So we're going to concentrate on a network analyzer. A vector just means phase. So when I looked at the internet, I found all kinds of vector network analyzers, such as this one. I thought, whoa, that's really cool. Now, I'm a retired physics professor. I never got to play with one of these. I'd love to have one of these in my shack, but this cost about as much as my automobile, so tens of thousands of dollars. I'm not going to get one of these as a hobbyist. Then I saw this one and I thought, oh, this is just way too cool. This cost more than my house. Now, I gave this talk back in December to a radio club down in Washington, D.C., and one of the hams in the Nano presentation, when I showed this slide, he interrupted me and said, "Oh, Barry, I have one of these." And I said, wait, you have one of these? This is a $250,000 thing. He said, yeah, at work. I said, at work you use one of these? Wow. I just looked at the slide and I'm drooling at this thing. Look at all this can do. I said, what do you do? He said, well, I align the radar systems on F-22 jets for the U.S. Navy. I said, oh, wow, that must be a great job. So do you get to take this home at night and check out your antennas? He said, no, Barry, we can't do that. But he said, I don't like to mix work and pleasure either. Oh, what an answer. But so he knew all about this. So I asked him some questions after the Zoom. But look at this. This is another kind of vector network analyzer. Also goes up to 20 gigahertz. So that's why it's useful on, radar systems on fighter jets. So here's the one we're talking about, the Nano VNA. It still does much of what this one can do. Not all, obviously. Not as accurately and not at high a frequency, but it is very capable. Nano VNA. Nano just means what? Small. So it has a USB connector, so you can get power to power up a battery or connect it to your computer. It has 2 ports. You might call it channel 0 and 1. I just call it channel 1, channel 2. One sends the signal out and can look for the reflection. So it's an out and an in. The other is just an in. So if you want to measure through something, you go out channel 0 through the device into channel 1. It also has 4 different colors. That makes it way cool. And it's also a touch screen. So it's fun to play with this. I found at my age and my eyes, you need bifocals to really see what you're hunting here. Probably the biggest restriction on the ones available right now is the internal memory. But I remember when computers came out, like had an Apple II back in 1980. It had 48K memory, and I thought, wow, 48K memory. That's a lot. You never need more than that. And it's a 48K. So right now, internally, it can save 100 data points. And I think some of the newer ones can save 200 or 400. What does that mean? Well, I'll show you. This has to be calibrated over some frequency range. And the calibration files, where you store what's happening between these 2 ports at different frequencies. If you connect it to a computer, you're not limited by that 100 data points, and you can use thousands of data points to calibrate over 2 meters, 440, 80 meters, whatever you want. I'll show you what that means. Has an internal battery, good for a couple hours. Take it out for a field day. The frequency range goes below 1 megahertz and above 1 gigahertz, and the better ones can go up to about 3 gigahertz, but I don't play with it up there. So it's kind of amazing for, American $50, $100. What is this calibration all about? The calibration is absolutely essential. Absolutely essential. And that's because when you look at this gadget that sends out a signal, it goes out over a piece of coax or a feed line, and it comes back. So the feed line changes the impedance depending on what frequency and what's the characteristics of the impedance. So you have to calibrate this either right on the device or at the end of some length of coax or some feed line you're going to use. You also have to calibrate it over whatever frequency range you want to use it. So when I do it, I make a calibration across 80 meters, 3.5 to 4 megahertz. Then I save that calibration. Or I do it over 40 meters or 2 meters or whatever it is. And each time I do a calibration, I save it on the computer. So someone said, every time you pick this up, you have to calibrate it. No, because I did that once, 3 months ago. And I save all the calibration information, not on the device. Here's the device. Oops. Instead of saving all the calibration on here, I just save it on my computer hard drive. Okay, so calibration is essential, and I'll show you why. So the other thing is these have little SMA connectors at the ends, which aren't very useful. So I purchased these extra little connectors that go from SMA out to the SO239 type things. That's perfectly adequate for 80, 40, 20, 10 meters. when you get to 440 megahertz, people realize, you know, these connectors aren't truly 50 ohms anymore. So it's not a good connection when you're working at higher and higher frequencies. But, you know, for the HF bands, these are fine. Another $10. So let's talk about calibration. All right. So when this Nano VNA arrived at my doorstep, I remember I didn't buy it. It had in the kit these 3 gadgets called calibration standards. So these screw into the ends of the Nano VNA SMA connectors. One said S, one said O, one said L. S, that's a short. It means there's just a wire connecting the pin and the braid. So that's 0 ohms. The O is an open, meaning the pin and the braid don't touch. It's infinite resistance. Another connector. Here's the critical one, the L. The L, inside this, the load, is a higher precision 50 ohm resistor. No inductance. So there's where your money is. Why do we want 50 ohms? Well, there's no particular magic about 50 other than radios usually have on the output 50 ohms, cables 50 ohms. So 50 has become, if you're working with coax, the kind of de facto standard since, I guess, World War II or so. So these little connectors screw in the ends and you calibrate your device. I'll show you what that means. So I just want to touch the surface of a Smith chart. Think of a Smith chart as a just resistance reactance graph. Because it's polar coordinates, don't worry about that. We can talk more about that if you invite me back for part 2. But 0 plots on the far left. 0. That means no resistance, a short circuit. Infinite resistance plots over here on the far right, or, you know, thousands and thousands of ohms. This is ohms. The key is that 50 ohms plots, we're going to plot 50 ohms right in the center, in the bullseye. How are we going to do that? That's the next step. Now, what about what's up here and what's down here? That's what's called reactance. So this is the resistance reactance, and the vertical, the departure from the horizontal, is either inductive or capacitive reactance. What's reactance? Reactance just means it's a kind of thing that a capacitor or a coil behaves. It's changing the timing, the phase. So here's our resistance axis, 0. So I plug in my little 0 standard, and I say to the Nano V, calibrate. I press the calibrate button. And the Nano VNA shows me a Smith chart and plots it right here. So I've taught my Nano VNA at this frequency that 0 ohms plots right here. That's my one standard so far. Then I unscrew it and plug in the open, and the open plots on the Smith chart over here. Not up here and not over here. It plots right here. Why? Because I want my open to indicate no reactance, but infinite resistance, whatever infinite means, you know, for us. So my Nano VNA says, okay, and it plots it on the Smith chart. So again, this is a chart from my Nano VNA working through my computer on a piece of software called NanoVNA Saver. You can do this right on the device itself, but the screens are much smaller, and you got to poke with a little pointer and get all your screens right. It was easier for me with my eyes to use the computer program to calibrate. Here's the key. I screw in the L, the load, and I say, okay, here's my 50 ohm load, calibrate. And it plots 50 ohms, no reactance, right here dead center. So the prime center on a Smith chart, you'll often see, if you look at these, it's got the number 1. But what we've done is just now calibrated the center of the Smith chart, the bullseye, to represent 50 ohm load. Load meaning the resistor that I plugged in. I could have picked 75 ohms, and then I'd make my Smith chart with 75, the bullseye, or 600 ohms, or any value. Doesn't matter. But for most of the stuff we do as hams, we're working with 50 ohm output transmitters and 50 ohm coax. Okay, so far? Okay, so
Yes,
remember.
yeah, good.
So remember, part 2, I'll talk more about what the Smith chart is all about. But for right now, I just want to say the center, the bullseye, is where I want to be. That is where I want my antenna to be. 50 ohms load to make my radio happy. Okay, so I'll just show you one more. I almost deleted this 10 minutes ago. I thought I don't need to do this. Up here is what's called inductive reactance. Well, that's just a name. What does it mean? It means the voltage and the current aren't in phase any longer. Something's getting ahead or behind something else. And down here, it's capacitive reactance. Again, something's getting ahead, or the voltage and the current aren't doing up and down together. Antennas can behave more like capacitors or inductors, as well as having a resistance. So when I look at the Smith chart and look at a given antenna, it could plot anywhere on this chart. Ideally, if my antenna plots just in the bullseye, I'm really happy, because you can't get any better than that. The bullseye represents an SWR of 1 to 1, or just 1. So that's what reactance is. Now, this is all in ohms, okay? This isn't labeled SWR or other things. This is ohms. So up here, J10 means 10 ohms, reactance. 25 ohms, reactance, 50. So the higher the reactance, the more I'm going here, what, clockwise. Down here, I have capacitive reactance. And the more I have, 10 ohms, 25, the J just indicates it's the other axis. It's just a letter, a vector symbol. So if my antenna is over here, I'm in big doo-doo, right? Really high resistance, really high reactance. That's not going to work well with 50 ohm coax. And if I'm down here, it's not going to work well, because if my antenna is 10 ohms and my coax is 50 ohms, that's a bad mismatch. So the idea is for my antenna to end up somehow, by magic or otherwise, in the center here. So I just want to show a couple plots. 50 ohms, resistance, no reactance, bullseye. Perfect. Up here, 10 plus J25. That means 10 ohms resistance, 25 ohms reactance. That would not be good on an antenna. Really hard to match the coax, but it could happen. 5 plus J50, it's like, yikes. That's like a 10-foot antenna on 80 meters. That would be something like this. It's just not going to behave well on a band like 80 meters if the whole antenna is only 5 feet long, 1 or 2 meters long. So resistance, that's the easy one, horizontal axis. Reactance, up and down. Neither is good. A typical Smith chart with an antenna that has a 2 to 1 SWR, and this is as complicated as I'm going to get in part 1. It could plot anywhere on this circle. By it, I mean my antenna. If my antenna has an impedance anywhere on this circle, anywhere, it has an SWR of 2 to 1. And that's not all that bad on 50 ohm coax. A lot of radios will still work fine if the mismatch is a SWR of 2 to 1. But each point here has a different impedance. Now, what does that mean? It means here, if I'm here, I have a resistance of, well, if this is 50 and this is a half, my resistance is 25 ohms here. Not very good. If I'm over here, where's my cursor? Lost my cursor. Here. If I'm over here, I'm farther from the bullseye. The resistance is 50 times 2, 100 ohms. So either 25 ohms or 100 ohms gives me the identical SWR, but two different impedance values. If I'm up here, somewhere here, I've got a combination of resistance and reactance. Down here, a combination of resistance and reactance. Not so bad. An SWR 2 to 1, it's not perfect, but I could live with that. My radio might work fine. I could work stations all over the world. But remember, where I'd like to be, my wish is, let's get in the bullseye antenna. Okay, so far? So our goal is, why is our goal that? Our goal is to get the maximum power radiated. We want to match the radio to the feed line to the antenna. Why do we want to do that? Because that's the maximum power transfer. So that's like a fundamental theorem 101. Maximum power transfer is when you match the impedances between radio, feed line, and antenna. And then I came across an ad for this NanoVNA, and I thought, oh, I'd like to get this one, but it was over $100 US, so I'm not buying it yet. But the new ones are coming out with N connectors. They're a little more rugged. They're coming out with metal cases. I like that. And they're just coming out a little bit higher in frequency, a little better quality, a little better firmware. But now they're over $100 US, so you get a little bit more, you pay a little more. So the best question is, why do you want one of these? Well, I love to play with gadgets, and in my case, I didn't even buy it. It was a present. So why would I want one? Well, I'll learn how to use it like any tool and see what I can discover. What I realized is I had to learn a lot more about some fundamentals once I had this in my possession. So let's take a look at why I would want a Nano VNA, or why you might, and I think some of you already bought one. Well, I have some of these. Aren't these good enough? Oh, well, they are pretty good. This tells me the forward power and the reflected power, and where these cross, it gives me something else called SWR, as if I knew what that meant. I know an SWR of a low number is better than an SWR of a high number. Why? It means the mismatch is less if the number is closer to 1. Can I do better than 1? No, 1 is perfect. The thing this doesn't tell me is, let's say my SWR is 3. How do I correct that? This doesn't tell me information about that. So it's not as reliable to me as the Nano VNA. And this thing might cost more than $50 itself. There's a lot of meters that are set up something like this with cross needles. So let's say I have my antenna and I put an SWR meter right at the antenna junction up here. And then down in my shack I have another SWR meter. And let's just say I'm operating on 80 meters. And I have someone transmit. I climb up my tower and I look, and this SWR meter says 2. And I come back down in my shack and this WR meter says 2. And I'm thinking, wait a minute, they both say 2. One's up at the antenna, one's down here. Why? So let me pause and ask you folks to unmute, hit the space bar. Can anyone tell me, why does an SWR meter read the same value whether my meter is at the antenna or in my shack? I'm assuming the feed line is pretty low loss, like good quality RG213. I mean, it's not 1,000 feet of coax, because then this wouldn't be true. So unmute and let me know, why is the SWR the same up at the antenna and in my shack?
Well, it's always measured at the feed point.
I heard measure it at the feed point. I'm asking if the SWR meter reads the same value, let's say 2, at both locations. Does that surprise you?
No, because it's not taking into account the feeder, is it? It's only what I'm saying is it's only measuring it at the feed point, not taking into account the feeder.
Okay, so this meter is telling me forward power, reflected power, and something called SWR. The meter down in my shack, let's say it's the identical meter, I have this at both locations, reads the same exact number. Does that surprise you that even at the end of the feed line on 80 meters, both meters tell me 2 to 1? They don't tell me how to make it better, but they both read 2 to 1. Does that surprise you?
No, it doesn't.
Okay.
Is it average?
Okay, so we should look at, so what's the meter really telling me if it says SWR? So there are a lot of meters that look like this. I have this one. In fact, I've got 2 of these. These are called antenna analyzers. A lot of people use them. They're fantastic. Battery operated, digital calibration. This one even shows me a little graph. This one shows an analog and a digital. But one of the problems is these are all hundreds of dollars worth of stuff. They're very nice stethoscopes, very nice. I'd prefer to have this Nano VNA over any of these 3. I'll show you why. But these work well for what the intended purpose is. So why do I want to use a Nano VNA? All right, I want to check out coax. I want to check out filters, and I want to check out antennas. So that's where we're going to end this part 1, taking a look at measuring coax for breaks, for attenuation, looking at how I can measure different kinds of filters, and checking out the antennas I have in my backyard. That's what I want to do in the next 40 minutes or 30 minutes. So let's measure some coax length. So here's my Nano VNA, and I have a little SMA output, and I have some unknown cable length, whatever it is. But it's, coaxial cable. So I set this up to do something called a time domain reflectometer, TDR. Now I could do this with oscilloscopes and signal generators 30 years ago, but it took some pretty clunky equipment to do this. This little Nano VNA can do it in seconds with a lot more accuracy, and it has a slightly different methodology to it. But think about it this way. What if it sends a signal down a coax cable, and just like the bat and the dolphin, it waits to get an echo? Well, what if it gets no echo? Then it thinks the cable is how long? Infinitely long. Nothing ever came back. Or maybe the cable was terminated in 50 ohms, in which case no signal came back. So I can't tell how long the cable is, right? If nothing comes back, I don't know how. It's like going yo in front of a wall and I don't hear an echo. I don't know how far the wall is. But what if I do get a signal back? So what if my cable, instead of terminated in 50 ohms, what if my cable here is terminated in 0 ohms? In other words, at the end of the cable, I just take a little connector or aluminum foil or something, just short the center and the braid at the end of the cable. So here I have a cable. One end goes to the VNA, the other end, well, I just did it in my shack here. I had about 50 feet of RG8X or something. So I just short the end. What happens when my signal gets to the end of the cable? It sees a short. Now, short isn't very good. So all the energy reflects back. So it's like, yo, yo. So all this gadget needs to do is convert the signal to time, and say, oh, the signal's coming back in 2 nanoseconds or something. It needs to know one more thing to be intelligent. What's the cable? Different cables, the speed of a radio wave goes at different speeds, called velocity factor. So in my case, I hook up this little $50 Nano VNA, and I tell my software, I've got Belden RG8X number 9258, and the software knows the velocity factor is 0.82. That's built into the software, not the Nano VNA. So my Nano VNA sends a little signal down, and bloop, look at this, 17 meters down the cable, meaning so many microseconds, or nanoseconds, or actually picoseconds, it gets an echo. The bat just heard an echo here. So knowing the kind of cable and the time, it can convert the time to distance, right? Because distance is speed times time. Oh, 17 meters. So my cable must be about 17 meters. So that's about what, 56 feet long. Did anything happen before that? No. So I have no breaks in the cable. Oh, good. So my cable's good. So good. This cable's sitting behind me. Maybe I want to hook it up to an antenna. But I'm thinking, well, RG8X, that's kind of small cable. Do I want to use that on a new 2-meter beam? 440? Nah. Where could I use this? So now I take my Nano VNA and say, well, let's change the frequency from 0.1 or 1 megahertz to 100 megahertz and see what comes back at different frequencies. So now I've set it up in a very different way. I'm still using the in and the out port. So I ping it and wait for an echo. The Nano VNA measures the reflected voltage, compares it to the forward voltage, and comes up with a ratio. It says, okay, in dB loss, I'm losing at 1 megahertz about half a decibel. I don't care about half a decibel. That's about 5%. No one would worry about that. How about at 80 meters? I'm still losing like less than 1 dB. Who cares? How about here at 10 meters? Now I'm losing 2 dB. Oh, no, that's like 30%. I don't care about a 2 dB loss. I could use this on 10 meters, 50 feet long. How about here on 6 meters? Well, now I'm starting to worry a little bit. 6 meters, my loss is 3 dB. 3 is a magic number, if you remember the log of, in the terms of logarithms. I'm losing half the voltage. Half the voltage? That's not very good. Half the voltage is not coming back. Well, where did it go? It got lost in the cable. What do you mean lost? It got converted to heat. So the current in the cable is just making an I squared R loss. I'm warming up the cable. Well, that's not going to radiate a signal, so I'm thinking, hey, this cable's probably good on 80 and 40 meters. Maybe I could cut it up and use it in a car, with 10 feet of it. But I'm not going to hook up this to my 6-meter antenna. How about 2 meters? No. Now the loss is like 6, 8, 10 dB. So I thought, oh, this is pretty cool. My Nano VNA just tested my random length of RG8 cable over this. Now, if you want to know why it's bouncing around a little bit, that's part 2. That's a 12th grade question. So, what else can I do with this Nano VNA? I'm having fun so far. I just tested some old coax. I want to test some inductors and capacitors. Now, what does that mean? Well, inductors and capacitors don't absorb energy. They just store it and re-radiate it. Capacitor stores energy in an electric field. A coil or inductor stores energy in a magnetic field, but it just gives it right back. So let's take a look at how filters are designed. So I want to take a moment, not too long, and take a look at filters. What's a filter? Well, I know what resistance is. Oh, ohm. Something resists. It obstructs. It's in the way. What's a reactance? Well, reactance is sort of an AC resistance done by coils and capacitors. We just give it another word. What's impedance? Yeah, my 9th graders would call it impedance. Impedance is a combination of resistance and reactance. And what's phase? Phase is timing. Timing. So without getting too involved, actually a lot of these are physics equations that I recognize. So let's a quick digression, not too far, because I want to get back to the Nano VNA. Coils and capacitors, how do they behave, and how can my Nano VNA support my understanding of these gadgets? So let's look at a coil. What's a coil? Well, it's what it says. It's a coil of wire, right? So if I hook this up to a battery, no problem. When current goes through this, it makes a magnetic field, makes a little electromagnet. In fact, the ninth graders I taught had fun getting batteries and wires and, just making little electromagnets, picking up things, having Star Wars duels and stuff like this. But when you hook it up to an AC source, now it behaves in a little different way. AC, that means the current's changing direction, right? So when the current goes one way in an inductor, it makes a magnetic field. If the current should change direction, that magnetic field's opposing the new current. So the magnetic field has to collapse to zero and rebuild back up in the other direction. Sort of north, south, south, north, north, south. The faster I switch the current direction, the more this thing opposes that current, resists it. And I would tell the ninth graders, do this. Hold up your finger and just wag your finger back and forth. I can do that easily, real fast. Not much inertia in one finger, right? All right. Do it from your wrist. So this is the inductance kind of my wrist, my hand. All right. Now do the same thing from your elbow. That's harder to do. That hurts. I can't do that as fast. All right. Now do it from your shoulder. Oh, I just hurt my shoulder. That really hurts. So when current tries to switch directions rapidly through an inductor, the inductor says, no way, no, no, no. The inductor resists, except we just call it reactance. So as the frequency gets higher, right, the current gets less because the resistance or inductor reactant gets higher. Look at this graph, and we all had to kind of learn this for our ham tests, but does that make sense? Coils allow low frequencies to get through the coil much more easily than high frequencies. I'm talking about radio frequencies, not sound. Does that make sense? I mean, there are formulas for all this, but I'm just looking at it as a third grader. We okay with inductive reactance? So what's inductance? Inductance is just describing the property of this that has that reactance. So the inductance of the coil depends on how tightly the coils are wound, what's the diameter, what's it made out of, a whole bunch of things, the length of the coil. Here's two coils. This probably has an inductance up in the hundreds of microhenries, and this is probably 10 or something. But the bigger the coil, the closer the windings, the more this thing is inductive. How about capacitors? I don't know why my ninth graders would call these capacitators. Capacitors, they work on a completely different principle. So on a capacitor, you have two conductors separated by an insulator, a dielectric. Could be a vacuum, could be plastic, glass, something. So charge goes in one plate, and a different charge comes off the other plate. So capacitors store this energy in the electric field between the two plates. What does that mean? Well, think of a capacitor like pumping up a tire. If you pump up a tire, it's easy at first, right? The tire's flat, you go pump, 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 pump. And the more pressure you get in the tire, the more you have to press to get that extra pressure. That's the way capacitors behave. The more you throw charge onto a capacitor, the more difficult it is to throw additional charge on the capacitor, just like pumping up a tire. Now, I asked a ham group this, and I got some interesting results. Charge a capacitor, whatever that means. You charge up a capacitor with a battery or something. When a capacitor is charged, what's the net charge on the capacitor? What's the net charge on a charged capacitor? Could you someone unmute and call out? Plus, minus, whatever you think.
0.
I heard 0. Any other ideas? What's the net charge on a charged capacitor?
Positive.
John's about to say something and I missed it.
I reckon it's positive.
Positive. So how does a capacitor charge? So I challenged my ninth grade class to come up with a skit. They're creative. Come up with a skit to describe charging a capacitor. And they were ingenious. So they came in, a group of 4 kids, and they had 5 minutes to show us their skit, how it charged. So they came in with this big box, like a refrigerator box. They carried it up the stairs and into the class. And they set it down. And on one side was a hole. And on the opposite side, there was a hole. And we all had to kind of look the other way. And one of the students that was in the group crawled inside the box. We didn't know that. Well, most of us didn't know that. Anyway, so they said, here's how a capacitor charges. So one of the students came to the box, walking towards the box with a yellow tennis ball, and threw the yellow tennis ball inside the hole. So the tennis ball went in the box. And about 2 seconds later, a blue tennis ball came out the other side. So that was kind of interesting. A yellow tennis ball went in and a blue tennis ball went out. So then a student came over with another and another. So every time one yellow ball went in, one blue ball went out. And, you know, time ran out, 1 minute, whatever it was. They said, that's our skit. So I thought, that was ingenious, because what did they show? For every electron that comes onto one of the plates, a different electron goes off the other plate. One goes in, one goes out. The one that goes in, well, that plate becomes what? More and more negative, because it's accumulating negative charge, the electrons. What about the other plate? It's losing its negative charges. They're leaving the box. They're going somewhere. So the top plate is positive. The bottom plate is negative. What's the net charge? 0. I thought, you guys get an A+. That was creative. So what's this got to do with the Nano VNA? We're going to test what goes in and out of the capacitor. So realize this. If you can switch very quickly, you know, the balls are going one way, then the balls are going the other. If you can switch very quickly, in a sense, might think about it this way, the capacitor doesn't run out of electrons. All right? As the plates become more and more charged, one plate's negative, one's positive, that creates a back voltage that's pushing additional charge away. Just like pumping up a tire, it's hard to pump up that last little bit of pressure. All right, so for a capacitor, the higher the frequency, the more current. That's the opposite of an inductor, meaning the capacitive reactance, the resistance of the capacitor, decreases with frequency. Oh, that's the opposite of the coil. Remember, here's the coil. The current's low at high frequency. Here, the current's high at high frequency. So there's probably, with a combination of a coil and a capacitor, some value where these two graphs cross. Magic. What do we call that? Resonance. If you know the L and the C and the capacitor, there's a formula to figure it out. That's not important for our purpose. But there's sort of a moderate frequency here that we call the resonant frequency of a combination L and C. How about antennas? Do antennas have L and C in them? Yes. Let's look at where that happens. So if we have a tuned circuit that has an L and a C, and we hook them up this way, side by side, we say we have a parallel circuit. But if we hook them up this way, end to end, back to back, we have a series circuit. These two behave in completely different ways. Yet the resonant frequency is the same if the L and the C is the same. What does that mean for an antenna? So what if we hook up these two in series? And I say, okay, I want to hook these up to a signal generator, my Nano VNA. And I start at a low frequency like 1 megahertz. We find 1 megahertz just can't get through the capacitor. It can get through the coil, but to complete the circuit, it's got to get through both. So low frequencies can't get through here because the capacitor is saying no way. What about really high frequencies? High frequencies can't get through the coil. They can get through the capacitor fine, but you got to get through both of these. What does that mean? High frequencies can't get through the circuit. So very low and very high frequencies have a high impedance, AC resistance. At some moderate frequency down here, it gets through the C and it gets through the L. But if you get too high, it resists more. So the impedance graph looks like this for a series LC circuit. What does that mean for the amplitude of the current? The amplitude is maximum at the resonant frequency. That's key. In a series circuit, the amplitude is maximum, meaning the most current, at the resonant frequency. That's the way antennas behave. But how about this parallel circuit? Well, in a parallel circuit, it's very different, isn't it? The current, when it gets to here, it sees a junction. So the electrons, the current, can either get through the L or get through the C. They have a choice. I'm not saying they're, knowledgeable about which way to go, but they try to go both ways. I'm hearing some sound from someone. Can someone mute? I'm hearing sound feedback here. Is it Derek? Someone. I don't know who.
It.
Okay. So what's happening here in parallel? The current, it has a choice. Low frequencies, not a problem. Go through the coil. High frequencies, not a problem. Go through the capacitor. Moderate frequencies, can't get through either well. So here at the resonant frequency, what happens? At the resonant frequency, the impedance is maximum. That means the resonant frequency is hard to get through this thing. The current, low frequencies get through. High frequencies get through. The resonant frequency, no, it's blocked. Well, that might have some useful functions for us as hams, right? We call them notch filters and other things. So let's come back to the Nano VNA and an antenna. Can a Nano VNA tell us the resonance of a circuit? Yes, otherwise I wouldn't have spent the last 10 minutes talking about this. So let's look at this gadget. What is this? Well, it's a device that says duplexer. Actually, it's a diplexer, but that's okay. Made by Comet. It says common, so you connect maybe your radio here. But here it says connect something 1.3 to 170 megahertz. Here it says, 350. So this is a VHF or HF connector. This is a UHF connector. What's inside this gadget? How does it work? So if you pry it open and look at it, here's the circuit. Well, what is this? So in series, there are inductors. Well, what did we say? Low frequencies can get through inductors, but not high frequencies. The capacitor is going to ground. It grounds the highest frequencies and allows the lowest frequencies. So this path might allow 2-meter frequencies, 145 megahertz, to pass through. This other choice, remember this is in parallel here. Capacitors. Capacitors block the low frequencies, but the high frequencies get through. And look, now the low frequencies are going to ground. So, what can come out of this circuit is the higher frequencies, here are the lower frequencies. So that's what this is designed to do. It separates the VHF and the UHF signals. Well, why would I want to do that? Maybe I have one transmitter and 2 different antennas. So I don't have to get on the back of the rig and unplug the jacks and plug in different antennas. I let this do the switching for me. So I hook up my Nano VNA to here, right? And I see what goes through this port. So now I have to hook this up as an in and an out. What gets through this? So here's what gets through the 2-meter port. Well, look at the scale, 100 to 200 megahertz. So the frequencies up to about 170 megahertz get through the 2-meter port. What about the higher frequencies? No, look, here's the gain. The gain is negative 30. Negative 30 means it's attenuating, right? The 30 dB, that's 10 to the 3, that's 1,000. I'm losing 1,000 factor, 30 dB. So at 440 over here, look, there's no energy coming through with a 440 megahertz on the 2-meter port. It's being isolated by about 35 dB. That's a lot. So this is doing what I expected. The 2-meter energy is coming out the 2-meter port, not the 440 port. How about the other? Here's the 440, the 70 centimeter port. It's blocking all this low frequency stuff. 2-meter, it's blocking, it's blocking by 70 dB. That's like, 10 million times. But anything above 300 megahertz, look. So I got this graph with my Nano VNA thinking, look at this. This gadget costs as much as the Nano VNA. I've just shown exactly how it works and how well it works and the dB. Thought, that's cool. That paid for itself. Now I dug out of my junk box this. I shouldn't call it my junk box, my storage bin. A Drake filter. This is called a low-pass filter. And I actually had one of these as a kid, and I just saved it. I don't use it anymore. I don't need it, but I saved it. Very clever gadget. What is it? How does it work? It's called a low-pass filter. Well, it says what it is. It passes the low frequencies. How does it do that? Low frequencies get through the inductors. Bing, 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 right through. If anything is higher frequency, it goes through here to a capacitor to ground. So what does that mean? This is grounding, eliminating the higher frequencies. How high? I don't know. Let's see. So I hook this thing up to my Nano VNA. Here it is. The out port goes through one end, through the filter. The other end of the filter goes around here to coax into the in port. Here's my Nano VNA. I set it up for what's called S21. That's the through signal. Here's what I get. This is so cool. Look at this. The S21 gain. The gain is 0. What do you mean 0? It means no gain, no loss, right? So 1, 2, and 3 are 10, 20, 30 megahertz. The low frequencies, the HF bands, get through this filter unattenuated. I mean, there's no amplification, but no attenuation. Great, I can use it on 80, 40, 20, 10 meters. So why do I need it? Oh, look what it does to the frequencies above 40 megahertz. It annihilates them here by 80 dB. 80, that's 100 million. So what happens? If my transmitter inadvertently, especially back in the 1960s, was generating any harmonic energy, unwanted, on the analog TV channels in America, channels, 3, 4, 5, 6, 10, I could get into my neighbor's television, and, that's no way to make friends. And I was a ham as a 13-year-old. Oh, man, I don't want to interfere with my neighbor's televisions. So if I insert this filter between my HF rig and my antenna, I eliminate the harmonics. And I thought, wow, this little Nano VNA proved how this gadget works. I kind of knew how it worked, but it was fun to get the graph. All right, a couple more examples. So look at this. I found this in my junk box. I have no idea what it is. Looks to me like a 25 mmF. That's today we'd call it a 25 picofarad capacitor, and some coil of wire, and it's mounted in some plexiglass. So I thought, all right, let's see what happens here. I remember these things were called traps, and I didn't remember why as a kid. So I hook it up to some coax center connector. I ground the two shields together. So I make a little cable that looks like this. It took me 10 minutes. Now I'm thinking, all right, I'll hook this up to my Nano VNA, send a signal through. I'll see what comes through. What should come through? I don't know. That's why I had this Nano VNA. Let's see what gets through. So essentially, this is the block diagram of I've got the Nano VNA channel 1. The signal comes out channel 1. It goes to this little coil capacitor or in parallel, and the other end goes back to my in. So this is the circuit, and I'm curious. Let's try 1 to 30 megahertz and see what gets through this thing. What should get through a parallel tuned circuit? Remember I showed you a few minutes ago. This is a high impedance at what? At the resonant frequency. Oh, look at this. Is this cool? So here's the S21, the through signal, 0 dB. Well, marker 1 is at 80 meters. Marker 2, 40, 20. So what's happening here? Nothing's getting through. It's losing 60 dB. That's a million times. But look, the higher frequencies can get through. What is this frequency? Well, it's pretty close to 20 meters. It's actually resonant at about 14.8 megahertz. The RF's getting blocked by 65 dB. I mean, that's like it's losing everything. The low frequencies get through it. How? Oh, the low frequencies get through the coil. The high frequencies are getting through. How? Oh, the high frequencies gone through the capacitor. So I can use this to isolate and stop or trap 20 meter energy. Oh, curious. Why would I want to do that? Oh, how about something like this? I've heard of things called trap dipoles. I don't think they're called trapped ED. I think they're called trap. So what does that mean? It means with one wire coax feed line, I could put on different traps and have a multi-band antenna just by including wire and traps. So I've got a trap for 20 meters, another trap for 40 meters, and that's the end here. So this might work on 20, 40, and 80 meters, something like that. Why not just build an antenna for each band? Well, you might run out of wire, run out of space. Besides, the expensive part's my coax, besides my radio. The traps are easy to build. So this is very clever, and my Nano VNA convinced me, oh, look at this. This is a great 20-meter trap. In fact, it's mistuned a little, isn't it? It's a little high. How can I tune it better so it's, center frequency is 14.1? Oh, I could think that through and test it, but to do that, I'd have to open the plastic, and I didn't do that. So let's check out a couple more antennas, then I'm going to stop for questions. So I hook up channel 0 to a couple antennas I have. What I'm going to ask the VNA to do is measure resistance, reactance, impedance, phase, and I'll get to this later. Reflection coefficient. Hams don't talk about that. Return loss. Never heard of that. Oh, SWR. So let's see what happens. So here's a 2-band trap dipole. I don't have these other traps. I just have 2, 1 on each side, and the traps are 40 meters. Here's my traps. These are my traps. So what's a trap again? It's an LC parallel circuit. I don't see, where's the capacitor here? I'm looking, I see the coil. Well, notice this tubing and this tubing, they're different sizes, right? So this pipe and this pipe, they don't touch. There's an insulator between them, so it's a 2-conductor separated by an insulator, plastic or something. So that means the capacitor is between these two pipes inside here. Oh, so maybe this is tuned to one particular frequency and I can use it as a trap. So I put it up, get the antenna up, and I say to the dual band antenna, I'm going to test you, so let's take a look at SWR. At 10 to 1, that's awful, but that's down to 3 megahertz. How about on 80 meters? Oh, it's 1 to 1. Perfect. At about 3,700 kilohertz. Not very good over here, blah, blah, blah. Oh, and then look. It's back down to 1.2 to 1 on the 40 meter band. A little bit off here. So I thought, oh yeah, look at that. I guess my traps are working on 40 meters. Perfect. I've just verified my trap dipole, which I knew worked anyway. I've got this antenna in my backyard. This isn't a picture of mine, but mine looks like this. I've had mine for about 35 years. A Cushcraft R5. R5. Well, the 5 means 5 bands. How do you get 5 bands in one wire here? Oh, so you can barely see here this little black stuff. They're the traps. So a Cushcraft trap looks like a coil and a capacitor. I don't see a capacitor here. Well, it's just like coax cable. There's an inner conductor and an outer conductor and an insulator. They don't touch. So the capacitance is between these two connectors. That's in parallel. So here's a parallel LC circuit. It's a trap. How do you tune this thing? Well, you can change the coils, or better yet, you can change the overlap here. Or you can move this up and down. You can play with it in a couple different ways. All right, so I said, I'm going to hook my Nano VNA up to my Cushcraft R5. Let's see what I get. So I set it up on SWR because I know what that means. So look at this. The SWR is pretty awful at 12 megahertz. I'm not going to worry about that. On 20 meters, oh, look at that. The SWR is like 1.2 to 1. Great. I love that band. Then, oh, not so good, not so good. Here's 18 megahertz. Not real good, is it? About 2.5 to 1. Hey, look, it's better here. Oh, so my Nano VNA said, hey, if you want to make it better, I got to change this resonant point so it's closer to 18 megahertz. Well, how do I do that? I just move the trap up or down a little bit. And blah, 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 blah. Oh, here's, what is this, 15 meters. Oh, good. The SWR is like 2 to 1. That's great. 12 meters. I've never been on that band. 10 meters. So in other words, I've just verified, hey, my Cushcraft R5 ought to work well on all these bands, and I could probably make it work a little better on the 17 meter band here. I could also test these. Now, I don't have a slide showing because I've got, it's sort of like in alpha test mode. What if I hook this up to coax and put a 50 ohm resistor up here? What should I get back if my Nano VNA is down here? Nothing. So what's this balun doing? It's attempting to what? Take a balanced antenna and feed it with unbalanced coax. What does that mean? It means I'm sort of defying the laws of physics here. The shield and the center conductor are each getting half the energy, right? Half the current. But what if the current on the shield comes right back down on the shield? Then my feed line is part of the antenna. That's not good. So this device, the balun, is trying to prevent that, or some people call it a voltage balun. All right, and I'm going to end with just a couple more slides here. I've got in my backyard an 80 meter antenna. It looks like this. It's an inverted V, but that doesn't matter. I've had this up a couple of years. I feed it with good quality 150 feet of RG213. That's like $150 American. That's the expensive part. Has a W2DU current balun up here. That's another 50 bucks. How many bands can I work this on this? I know I set it up for 80 meters. Let's test it with my Nano VNA. So I check it out from 3 megahertz to 30 megahertz. So what's the SWR? Well, right about here, it's 1 to 1 at 3.6 megahertz. Beautiful. I love to work that part of the 80 meter band. Then up around 7 megahertz, 40 meters. Oh, no. The SWR is about 7 to 1. That's no good. I'm not going to use that with coax on 40 meters. Blah, blah. Oh, look at it down here. This is beautiful. Look at this. The SWR is back to about 1.2 to 1. Oh, but wait a minute. That's about 11.8 megahertz. I don't have a license to operate there. That's no good. How about over here? No, no, no. Oh, look at this. Beautiful. SWR is low again at 19.2 megahertz. Bummer. I don't have a license to operate there. That's not a ham band. How about 15 meters? Well, it's about 2.5 to 1. Not great. Not great here either. So what have I learned here? Oh, it does have multiple resonances, but only one of them's in the ham band that'll match my 50 ohm coax. So this is essentially, if I feed it with coax, what? A one band antenna. Oh, I kind of knew that when I put it up. So here's my 80-meter dipole with my Nano VNA, but now I'm going to show you all 6 graphs, and this is getting a little into the weeds, I realize. Here's my Smith chart. Remember, where do I want to be? The bullseye. Here's my SWR, and here's where it's lowest, about 3.6 megahertz. That's good. Here's my phase measurement. Remember I said, oh, I'm going to show you a phase graph. What's this telling me? It's going from capacitive reactance to inductive reactance right around 3600 kilohertz. Why would it do that? Because that's where the L and the C are resonant. So this antenna, 150 feet away, is resonant right at about 3600 kilohertz. I love it because that's where I like to operate. My Nano VNA just confirmed what I thought I already kind of knew. So we're back to where I showed you. If I showed you this slide and said, if you have a Nano VNA and you hook it up to your antenna and you see this graph, can you interpret it? So let's go back and check. I think when I asked that, someone said the SWR should be lowest at 0.3. I wasn't sure if I remember that correctly. The SWR should be lowest if I feed it with 50 ohm coax. Where? In the bullseye. Why? Because that's where I calibrated this Nano VNA. So at position 2, 3.6 megahertz, I'm closest to the bullseye. I'm closest to 50 ohms resistance. The SWR is lowest if I've got a perfect match. So 2 is my ideal spot for this antenna. Well, what about 3? 3 doesn't look all that bad. It's still resistive. There's no reactance. But in terms of the resistance value, it might be 200 or 300 ohms here. So I have to say, you have to be careful after you say this. Position 3 is resonant at the end of my 150 feet of coax. But the SWR is going to be lousy. Why? I thought SWR is low at the resonant frequencies. No, no. I'm measuring the resonance 150 feet away from my antenna. What does that mean? It means my 150 feet of coax, because it has inductance and capacitance, is moving the impedance up and down and up and down and up and down. So 150 feet from the antenna, I now see 2 resonant points, 2 points where there's no reactance. But only one of them is good for a 50 ohm match, position 2. That took me a while to understand, and that was like an aha moment. Oh, resonance does not mean low SWR. Resonance just means no reactance. Okay, so remember I said, can you understand this graph? No one volunteered. What's happening here? The phase is going, here's 0 degrees. So at 3600 kilohertz, suddenly at that sharp point, the impedance is going from capacitive to inductive. Well, what does that mean? Well, essentially, it means that at 3600, the current and the voltage are in phase. Resonant, maximum current, maximum radiation. If I go below the resonant frequencies or above the resonant frequency, I'm a little off resonance. The SWR goes up, current, voltage are out of phase. But now from this graph, I can see how to correct it. How to correct it. What does that mean? I'm not going to go up and chop 10 feet off the wire off the antenna. How do I correct it in my shack? Oh, what do I need? I need an antenna tuner. And that gets us into part 2. So I think I'm going to stop the share, and I realize I went a little over, didn't I? Let me stop share. And I could go on for 3 more hours, but I need to stop and see if you folks have any questions based on what I showed you about this little $50 Nano VNA. So please unmute and call out comments or concerns or questions.
No, you've actually taught me to read a Smith chart, and I now know where to look at my 5/8 wave homebrew aerial and why I'm getting 25 ohms and a low SWR.
Now watch out when you say you're getting 25 ohms. You're measuring that in your shack, right?
Yeah, I'm getting...
And how many feet of coax is it to your antenna?
I would say it's about between 25 and 30 feet, roughly. But I'm also like that. That's at around 10 meters. But at 40 meters, I'm getting 50 ohms, but a very high SWR. So
okay, because a 5/8 wave is what? It's technically, well, all by itself is not resonant where you want it. It's a half wave would be resonant, a 1 wave would be resonant. So 5/8, you need a little matching coil at the base, especially if it's a vertical, right? So what are you trying to do there? You're trying to match 50 ohms coax. I'm assuming you have 50 ohm coax.
Yeah.
To the impedance of the 5/8 wave, which might be 80 or 90 ohms. So that little
Yeah,
matching coil is the key there. That's the L and the C.
Yeah,
So there your matching is trying to right at the base of the antenna, which makes sense.
yeah, it's got an open an RF choke and a matching stub. So now I know that I need to alter the matching stub, because it's it's a homebrew 5/8 wave. So yeah, I now know that I need to alter the matching stub to balance the impedance and get the SWR as low as possible, as well as getting it down to 50 ohms. So yeah, the Smith chart bit has taught me how I'm going to go about sorting that out. So yeah,
that was well said. And you can achieve the matching either right at the antenna or in your shack. Does it make a difference where you do it?
Yeah, well, yeah, we're doing it at the antenna. I'm going to be changing the matching stub, obviously. So yeah, and so yeah, no tuner required. All good.
Well, your tuner is right at the antenna. Your matching stub is a tuner.
Yeah.
So I said this before. What if my feed line, let's just pretend, had no attenuation? Let's just pretend. 0 attenuation. And let's say I have 100 feet or 200 feet, whatever it is. Does it make any difference whether I do the matching at the antenna, right at the feed line, or in my shack? No.
No, I don't suppose it does. No.
So what do we worry about? We shouldn't be worried about SWR. What we should be worried about, if even worried about anything, is what's the loss in your feed line for a given situation. If you're running a high SWR and running coax, like an 80-meter antenna operating on 40 meters, you're going to lose a considerable amount of power in your feed line as heat. That's no good. But if you have very, very low loss feed line, like ladder line, balance line, it's not essential then that your antenna itself be resonant. What's essential is the antenna system be resonant, and your coax, your feed line, is part of the antenna.
Yeah.
So I stopped because I was watching the clock here. The last 10 slides were trying to convince you, you don't want a resonant antenna. What you want is a resonant antenna system. And if you're working like I do a lot on 80 meters, if I match in the shack, it's just as good as matching out at the antenna. And it's much more convenient for me in the nice comfort of my shack to turn a couple dials. My radio's happy in either case if it sees 1-to-1, SWR. If my radio sees 50 ohms, it doesn't care what's out there. It could be a dummy load, it doesn't care. So the important thing is to remember this. The SWR on your feed line does not change if I mess with controls in my shack, although the impedance does, and my radio's happy. So an antenna tuner really ought to be called an antenna make my radio happy gadget. The only way to change the SWR on the feed line is to correct it at the junction of the feed line and the antenna. An SWR does not change on feed line unless I have like 1,000 feet of it, you know. So that's kind of into the weeds on part 2. The important thing about the Nano VNA is watch how you interpret it. What you're measuring in the shack. Well, I'll say it this way. Unless you have a half a wavelength of feed line, or 1 wavelength, or 1.5, unless you have an integer multiple of a half wavelength of feed line, what you measure in your shack is not what you would measure had you taken your VNA right to the antenna itself. They're not the same. The SWR will be the same, but not the impedance. That's kind of a sophisticated comment.
Yeah, got to follow in that, yeah.
Other questions or comments?
You're all being very quiet now, Barry.
Well, you know, that's what, you know, when you teach and you've got, you know, in my case, the kids right around, you know, I can stop and look at their faces and, you know, I can challenge them. But I like to teach, what's it called, Socratically, didactically. And they do the same to me. If I say something and say, wait a minute. They, by the way, they'd call me Teacher Barry at a Quaker boarding school. Teacher Barry, that made no sense. Go back and explain that again. You know, what is reactance again? You know, and actually, with 9th graders, I did teach them reactance and impedance, except they just wanted to get under my skin, so they'd call it impedance. But they had a sense that capacitors don't do the same as resistors, and inductors don't do the same. And when we designed little circuits, we designed them with sound waves, so it wasn't, you know, as dangerous as RF waves.
your question earlier on, Barry.
Yes.
When you've got the 2 meters measuring the same SWR at the feed point and at the rig end, do I take from what you've just been saying? Does it mean that the 2 meters are reading the same? Does it mean that the coax feeder must be half wavelength or half wave?
No. It doesn't matter. If I'm assuming this, the feed line is fairly low loss. I mean, granted, if I put in 1,000 feet of feed line, the SWR meter in your shack would read 1-to-1 because you've lost all the energy in the feed line. The impedance depends on the length of the feed line, and every half wave it duplicates itself, not the SWR. See, as a physicist, I say it this way: SWR is a scalar quantity, not a vector. It doesn't depend. SWR does not depend on the phasing. The phasing, the timing, is just the reactance. The impedance. See, if I go back, remember that's the Smith chart with the circle. When I go around the circle on the Smith chart, I'm going around to infinitely different impedances, but they all have the same SWR. Let me go back to screen share and come back to that, because that's kind of an important concept. Let's see. Let's see if I can get this. Somewhere back here when we talked about impedance. All right, whizzing through here. Whoop, 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 whoop. A faster way to do this. Can I go by it?
So it's almost like the feed line is becoming like near on invisible, but you've got a perfect connection between the radio and the antenna.
Here, this slide. Is this up now?
Yeah.
You see this?
Yeah.
Okay. So 1-to-1 SWR is only 1 point on the Smith chart, the bullseye. Just one little dot. 50 ohm resistance, no reactance. Let's say my antenna, wherever it is outside, lands somewhere on this circle. So it has some impedance different from 50 ohms resistance. What if it lands right here? Then my antenna is 25 ohms, because this is half of that, 0.51. I don't know if you can read that scale. 25 ohm resistance on my antenna would still give me a 2-to-1 SWR. Also over here, a 100 ohm resistance antenna would still give me a 2-to-1 SWR. My SWR meter can't tell me which it is. It just says forward power, reflected power, SWR is 2-to-1. With the Nano VNA, I can see exactly where I am on the impedance graph. In other words, the Nano VNA reads impedance. My little SWR meter does not. This tells me phase. The crude meters do not. They just tell me forward and reflected power. So what if I'm up here somewhere? And I'm measuring this in my shack. I'm up here. What if I cut off 20 feet of coax and just put my Nano VNA on my new coax? Would I still have an SWR of 2-to-1? Yes, but I wouldn't be here. I'd be maybe over here on the Smith chart. Every time I add or subtract coax, I'll move the impedance around this circle. But notice, I'm never getting closer to the bullseye. What does that mean? I'm not improving anything. Well, if I had a choice, someone asked me this, how much feed line should I use? And my answer was kind of silly. The shortest amount you need. Because other than that, you're just wasting it. Is there any advantage to have your feed line be half a wavelength? Not really.
I think it's one of the common myths on amateur radio, really, isn't it? About, I suppose it comes from antennas where the feed line is actually part of the antenna, but
that's true.
That's a whole different situation, then, isn't it?
Yeah. Oh, like an end-fed ZEP, it's really important. Yeah. No, but if I have an 80-meter dipole fed with coax, anywhere on this circle, my impedance, as I measured in my shack, anywhere is equally good for me. My radio's happy. It's not totally happy. I'd be happier if the SWR were 1-to-1, but only marginally so.
Yeah.
Some people get SWR kind of like, it has to be 1-to-1, and I'd say, why? Because then it's a perfect match. I said, well, what if I said, you're going to lose 1 dB, you're going to lose sleep? They say, I don't want to lose 1 dB. I said, 1 dB. That's 1/6 of an S unit. The guy on the other end won't know the difference. So how much are you willing to lose? And finally, I got someone to say, well, if I lose 1 whole S unit, if my signal goes from S8 to S7, I'm not going to be happy with that. And I said, okay.
Yeah.
So your attenuation, you're willing to take or lose 6 dB. That's 1 S unit. 6 dB, that's an SWR of like 5 or 6 to 1.
Well,
so I said, you know.
Yeah, it's one of the questions that so often comes up when people say, which coax should I buy? And it's a case of the best that you can afford for any given situation.
Yeah.
I would say what power level you're running first. If you're running high power, I'm not going to do that with RG8X.
No.
And also what frequency. If I'm on 440, I'm not going to use, you don't want to lose half your energy in the cable.
No. Well, I think that's the thing when people spend thousands of pounds on radios, hundreds or even thousands on antennas, and then sort of £20 on the cheapest coax they can, the cheapest RG58 they can find, and wonder why they're losing, most of their transmitted power.
And you have to realize it's reciprocal. You're losing it receive as well.
Yeah, well, exactly. Yeah, very good.
So how many of you already have one of these and you've started to play with it and have a fair understanding?
Yeah, I've only been able. Yeah, I've got one, but I've only been able to do like a band sweep or an SWR reading. But thanks to tonight, you've shown me how to do a bit more with it, with like an understanding Smith charts, and that's that is a massive help.
Mm.
The software that I finally got after about a month playing with this thing, someone said, well, why don't you get the Nano VNA Saver software? Yeah. And I said, what's that? And they said, you don't know about that? I said, no, I'm a rookie. I don't know about it. So I downloaded Nano VNA Saver, S-A-V-E-R, for Windows 10, free. Mm-hmm. And within 10 minutes, I got it working, and everything was so intuitive.
It is good. I started
and I could make all these pretty graphs with all these different colors at once. Yeah. Whereas the Nano VNA itself, that's a pretty small screen. Well, I'm afraid I'm going to drop this thing.
Yeah. I started off using the VNA-J software, but that's not the most intuitive. I don't know if you've used that.
Someone asked me too, did you download the latest firmware for this? Well, the Nano VNA itself generically has like 10 different manufacturers now. Mm. And they're all coming out of different factories. Some are higher quality. So, I have no idea where's a safe place to buy one of these and have it work right out of the box. But the one that was sent to me is almost a year old, and it came from Amazon. It's the Nano VNA H4, I think. It's not the newest and the fastest and the biggest screen and the best connectors. But I've had immense fun with it for almost a year now. It's never failed. I don't want to update the firmware thinking, I might mess it up and then I'm going to be in real big doo-doo. And I don't mess with it up at 1 and 2 and 3 gigahertz either. It can also measure resistance and reactance graphs and plot those. I didn't show you that. I really showed you Smith chart, SWR, and phase. But it can plot like 10 different kinds of graphs. And it can plot the impedance too. There are lots of ways to do it, to use it.
There's a lot of silence out there, but I can hear the cogs turning, trust me.
So for you folks, it's what, 9 p.m., 9 o'clock?
Yeah, right.
Yeah, in Pennsylvania, we call 9 p.m. Quaker midnight. It's like time to go to bed. Quaker midnight.
You mean they're all in bed?
Yeah.
But Zoom is great because, you don't have to drive to the meetings and park. And as I got older, I had trouble driving at night. Zoom is great. I miss the social time, coffee and donuts and stuff.
Where in Philadelphia are you? In Pennsylvania are you, Barry?
So I'm about 20 miles west of Philadelphia, Westchester, Pennsylvania.
I know it well. I used to live in Ardmore, Pennsylvania.
I grew up in Marion.
Oh, you're joking. Wow, okay.
Went to Lower Marion High School.
My wife went there. My wife went,
We're not the same age, or I'd say, what was her name? Maybe I know her.
no. She's got an older sister though, but I'm not sure.
I graduated high school in 1963.
Oh right, yeah, I think.
But I had my ham license in 1958. I was 13 years old when I got my general.
Oh,
I didn't know anything. I just passed all the tests by memorizing. Nobody knew, nobody cared. You know, it was just multiple choice. In fact, when I took the test, you had to draw a circuit. It said, draw the circuit of a one-tube Colpitts oscillator. And I knew you draw a circle, you put dots, you put a squiggly line. I drew the whole circuit. If the instructor had said, what's this circle? I'd say, I have no idea. I just know you draw a circle. That was, the valve, the tube. So it wasn't until, 30, 40, 50 years later, I knew what all these parts were.
Oh dear.
So if at any point you want to know the under the hood stuff, part 2, this has been fun. It's a great time for me. 2 in the afternoon, I'm wide awake.
Yeah.
Part 2 gets into much more, as I say, into the weeds. Yeah.
Excellent.
We'll have to get Sandra to arrange part 2 with you.
Yeah, either that or if you can send it to Dave and he can upload it on our website. Then
I could send you the whole PDF.
Yeah.
I usually over-prepare because I don't know what's going to come up as questions. So I showed you about half of all the slides I had made up.
Yeah,
No,
we'll get Sandra to arrange part 2.
Is Sandra here?
Yes.
Yeah.
I don't
She's
see her
muted.
picture.
Oh. You know,
Come on, Sandra.
There you go. I see you. Okay. Thank you for the emails. Thank you for the invitation. I've had fun.
It's been a pleasure, Barry. Thank you so much for doing the talk for us.
Yeah, definitely.
My first DX talk. It's great.
Yeah.
I'll second and third that. It's been enlightening, very enlightening.
Well, I figured it's a rookie teaching rookies, so that's the way I see it.
Sandra's our CW expert.
Each month I learn more because I learn, and I try something, and I thought, that doesn't work. I have a few contacts who are engineers who have corrected some of my errors. I said, thank you. See, a really good question for a ham group, something is so simple. Why does an antenna off resonance have a reactance? Why?
So I have to sit and work that one out.
So here's my analogy, and I didn't show you this. It's kind of part 2. So I'm at the age where I'm a grampy, and I've got grandkids, and we go to the park, and the grandkid right away jumps on the swing. What's my job? Push. I'm the pusher, right? So Grampy's pushing the kid on the swing. How does Grampy know when to push? Well, everybody knows that. Even the grandchild knows that. So the grandchild looks to me and says, Grampy, push in phase with my natural swinging on the swing, so you'll be in resonance with my frequency, or something like that. Well, she doesn't say it in those words, but what she means is, there's only one good time to push. So when you push, I go higher. And I'm thinking, she's just explained phase. If I push too soon, what happens? Well, I crash into her. It's like capacitive reactance. What if I push too late? Well, that's equally bad. I'm running after inductive reactance. So what is inductive and capacitive reactance? It's Grampy not pushing at the right time. Now, what's Grampy and grandchild on a swing? Do you see an end-fed dipole? That's what I see. Now you got it. So in an end-fed dipole, Grampy's the feed line. What's the feed line got to do? The feed line's got to push in sympathy with the natural vibrations of, well, not the kid on the swing, but the current on the antenna.
Yeah.
So if the antenna current isn't matching with Grampy, you've got an SWR problem. You've got a reactance problem. So why does an antenna have reactance? Because it's not the right length for the frequency you're trying to work on. There you go.
Yeah.
Then we can all see it.
Length of the antenna matches the frequency of the swing. So, yeah, the two match up. You get a perfect match.
Now, it doesn't mean you can't operate your radio off resonance. It's just your radio may need a little help to do that, like an antenna tuner or, matching coil on your 5/8 wave, something. But I like to think of Grampy as the feed line and the kid swinging back and forth as the current on the antenna. then it kind of, you know, we all see that
only makes the
mechanical
radio happy.
analogy.
Yeah, that only makes the radio happy. It doesn't. It doesn't put out the performance. It just makes the radio happy. But if you've got the two in harmony, like the length of the antenna with the frequency that's being operated, then both are in harmony, both are happy, and the antenna will radiate the maximum power of the radio.
Correct. But we can operate off resonance with, you know, slightly less efficiency, but not much, because our feed lines are never perfect. But like on 80 meters, I can operate on the whole 80 meter band and not worry about power lost in my cable. Because on 80 meters, the attenuation is something like 1 dB per 100 feet, you know.
Yeah.
So at most, with an SWR of like 5 to 1, 6 to 1, I'm going to lose another 1 dB. I don't care about 1 dB. That's 10%. Who cares? All these articles about broadbanding 80 meter antennas, I mean QST for America, it's like, who cares? On, you know, on 440 I care.
Yeah.
Maybe even on 10 meters I care, but not on 80 meters, because if I have decent coax, losing 1 dB or even 2 dB, they got the other end, that's a fraction of an S unit. They're not going to know.
Although I do know somebody that, depending on which part of the band on 80 meters he's working, he'll drop the aerial down and add or remove bits. He's got his CW.
No.
And he's
maybe just wants the exercise. Yeah.
Well, maybe. Yeah.
It's an ego boost of a 1-to-1 SWR, but the other guy at the other end, whoever you're talking to, they don't know.
No.
They either hear you or they don't. Yeah.
Yeah, I think it's always this sort of myth that it's apart from what gets lost as heat in the coax, when it's if reflected power gets the same percentage gets lost again, but then it goes back to the aerial again, and the same. So if you're only losing a fraction of a dB each time, then it's, as you say, it's minimal really each reflection.
I've had one local ham tell me my 80 meter antenna, you know, without an antenna tuner, my 80 meter antenna has an SWR of 1-to-1 across the whole band. And I said to him, interesting, that's impossible.
Yeah.
Physically, that's impossible. Unless maybe your antenna's a dummy load. Do you have a dummy load? He said, no, I've got a G62 RVX, you know, duplex, you know, and I spent $300 on it. And I said, I want to come over and see. Because there's no antenna. Now you can, you know, there's stagger tuning, there's cage dipoles, the W1AW does that. So instead of one number 12 wire, what if you put like 5 in parallel? So now it looks like you have a thicker wire. Well, yeah, a thicker wire will have lower change in SWR, but nothing is 1-to-1 across the whole 80 meter band. That is impossible.
Yeah, you're lucky to get a few K really, or a few kilohertz at exactly 1-to-1.
Yeah.
Good
so
evening.
antennas are mysterious. But the Nano VNA, I found for me personally, I had to relearn some things once I had it in my possession and tried to interpret what I'm seeing in my shaft.
Right, yeah.
So it's a useful tool. Better than my Swiss Army knife? I'm not sure.
Yeah, well, you need the Swiss Army knife to do the building, I suppose. That's the...
Yeah. I trim my coax with my Swiss Army knife. I can't trim my coax with my Nano VNA. But I am afraid it's going to fall. Protect it.
I've bought a few different sort of VNAs over the years, and yeah, I do like the Nano VNA, but I've got the one that's just the pair of sandwiched PCBs. Well, you know, which always looks like, yes, if you look at it the wrong way, it will break. Yeah. Like that one. Which
people ask me where should I buy one, and I don't know. So especially in Britain, I don't know, you know, who's the reliable supplier.
Yeah, Amazon really have. There are lots of different ones. Quite a few eBay suppliers as well. Though most of them ship from China. Yeah, well, or AliExpress. Yeah, but they all ship from China anyway. So
yeah. It's pretty much pot luck as to what you're going to get, and if you do get a good one, keep hold of the supplier name and keep using them and recommend them.
Yeah, but yeah, what you say about the firmware, that is a whole different ball game. There
Right.
are so many. There's so many different people that have created their own forks to do different things, extending the frequency range. Or yes, I tend to prefer to just use the standard stock firmware.
When I was studying astrophysics as a graduate student, I had one of my professors say this to me after we got to know each other very well. And he said it this way, and it's always stuck with me. He said, "Fireman," because he was Dutch. "Fireman," my last name. "Fireman, you worry too much about the third decimal point. If you concentrate all your energy on getting the third decimal point correct, you might miss the first decimal point." And he was a galactic astronomer.
Yeah.
So what he was saying is, don't worry too much about the nitty-gritty details. Step back and be sure you get the overall picture correct.
Yeah, definitely.
So who should I email the entire PDF to, David?
You can either email it to me or to Sandra. It doesn't really matter. Email it to me.
Okay. So you folks could take a look at the slides from the part 2, the in the weeds or under the hood, and let me know if however you can use those. They go into more gory detail.
Yeah, we'll get Sandra to arrange a date for part 2 with you, if that's okay.
Yeah, I'll arrange it with you, Barry, to do the second part of the talk. It's been very good tonight. Thank you very much.
Yeah,
I've enjoyed it.
second that.
Yes, thank you very much.
Definitely.
I
Very
shall
good.
have to now get my VNA out of the drawer that's it's hidden in somewhere.
Well, I didn't like mine until I downloaded the Nano VNA saver. Then I realized how easy it was to use it and save the files. And for me to see all these graphs on a big, 20-inch monitor, much better than a little 3-inch screen.
Yeah. I might have to look at one of the, like you were talking about, the SAA2N ones, the ones with the N type and a metal case. It just feels like you might be able to take that on a field day and not smash it.
Yes.
Oh.
Can I just say, absolute fascinating part 1. Looking forward to part 2.
Okay.
But I'd also like to welcome K3EUI, who's joined us from India. So it's been a real DX night tonight.
Yeah. No, I
Looks
saw
like
that.
the friend behind you has a question there. Looks like that.
I know,
that
he's just sitting there.
Oh,
He's got a car full.
that is so cute.
Show you the rest of the family if I can find it.
Yes, yes.
Can I ask, Barry, when you started to play around with it, was there any online resources you went to first of all just to see what each of the menu options did and to try and get the basics before you started to play around with it much? Or?
I wasted hours and hours watching YouTubes. There were a couple very good ones. To tell me what I could do and use it as a tool, that's what I was looking for. And somehow when I clicked on this or that, I got more RF engineers telling me what's inside of it, which didn't impress me because I wasn't interested in that. I think we have to watch out that when we use certain sophisticated words, that our audience understands what those words mean. So this little Nano VNA can measure something called reflection coefficient. That sounds simple. It calculates other things like SWR from the reflection coefficient, but it measures the reflection coefficient. What is that word? What does it mean? As a ham, I'd never heard that term, and I've been licensed over 60 years. So why didn't I know that term, reflection coefficient? It's just the ratio of the voltage reflected divided by the voltage sent out. It's just a ratio. So what if the voltage coming back is 0? There's nothing coming back. Then what's the reflection coefficient? 0 over anything is 0. So my ideal antenna, the ideal antenna would have a reflection coefficient 0. That translates to an SWR 1 to 1. Well, that sounds really good. That's easy to visualize. My antenna's not returning any energy back to the transmitter. It's radiating it all, even if it's a dummy load of it. So what if it reflects all the energy? What if the voltage reflected is just as big as the voltage going in? then V reflected over V forward is 1 over 1. Well, that's 1. So what if the reflection coefficient is the number 1? Well, that's the worst I can be. So in other words, my reflection coefficient is some ratio, some fraction between 0 and 1. 0 is a perfect antenna. 1 is a very imperfect antenna. But that's easy to know. It's a number between 0 and 1. What could be simpler? So what am I willing to accept as a reflected wave? Well, I remember it from SWR units. My radio didn't complain if the SWR was about maybe 2 to 1, 1.8 to 1, 1.5 to 1. It doesn't have to be 1 to 1. But once my SWR got to be on 80 meters, 3 to 1, my radio started complaining. Beep, 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 beep. It's no good, no good, no good. So it's easy to see the VNA as measuring reflection coefficient. And the one thing it does is measure the phase, the change in time, Grampy, the phase change between the reflected and the incident voltage. Why do you want to know phase? Reactance. So a lot of these gadgets that don't measure phase just measure the scalar quantity called SWR. That only tells you, well, it's a good match, it's not so good. Doesn't tell me anything about why it's not so good. The VNA, if I can interpret what it's doing inside, can tell me exactly what's not good about this particular antenna or this feed line. So that's why the $50 investment is so much better than a nice digital SWR meter or something. So it's sort of like, can we interpret what it's telling us to? And some of the videos that I watched to try to learn didn't teach me the 3rd grade level stuff. They were already at the beginning, up at the 9th or 12th grade level stuff, and using vocabulary as if I knew what it meant, and I didn't.
I think there's always a danger with any of those things, the assumption of the sort of readers or the viewers' knowledge, and if you don't get that, obviously everybody here has a different level, so it's a case of trying to pitch it at the point where you're going to lose as few people as possible.
Yeah, see, when I thought about giving a talk, I thought, well, I don't want to start too high. So I thought, oh, I remember, because I lived at a lake where there were bats. And the bat sending out sound waves and using the echolocation to eat food, that's what the Nano VNA does. But it uses an RF wave, not a sound wave. And then I thought, if it's discovering phase and reactance, what is phase anyway? And I thought of the analogy of Grampy and the grandchild on the swing, because we've all faced that. So we know we have to push at the right time. What does that mean? We have to push knowing how long it takes the grandkid to get back and forth. What if Grampy was blindfolded? How does Grampy now know when to push? You don't. The other interesting question someone asked me, and it was interesting, for a given length of wire for an antenna, how many frequencies are resonant? That was a good question. For a given length of wire, I'll just say 100 feet, how many frequencies, radio frequencies, can I make that be resonant on 100-foot wire? And the answer is?
As many as you want.
Yeah, infinite.
Yeah.
Infinite. Now, you can think of it like this. For any given wire, the ideal might be a half a wavelength, thinking about it as a dipole. Most of us have, for dipoles, a center-fed dipole. Does a dipole's resonant frequency change if instead of center feed, you end feed it? Does an end-fed dipole and a center-fed dipole of a given length, do they all show the same resonant frequency? Yeah, that's a good fundamental question, isn't it? And the answer is yes. The resonant frequency does not depend on where you feed the antenna. Center-fed, off-center-fed, end-fed. It does change the impedance at the point you feed it. Yes, of course, yeah. But the resonant frequency of a given length wire is only dependent on, well, you might say the length of the wire and also if there are any other wires nearby or ground or something. But in free space, a given length of a wire, you can force that to resonate on any frequency if you have the right matching, network, and if your attenuation is low. The guy who designed satellite antennas, Walt Maxwell, W2DU, wrote a book that was really one of the best books I've ever read, called Reflections, W2DU. And he wrote a lot of QST articles back in the 1970s. But he was talking about that fact that when he designed satellite antennas, they didn't have to be a certain given length. The feed line between the transmitter and the antenna was only like 2 inches long. So you want to design the antenna to work best on that satellite, but it doesn't have to be a quarter wave, half wave. 5/8 wave is kind of ideal for verticals because it just puts out a nice low angle signal. But any wire can be forced to resonate on any frequency with any sort of a matching network. So a couple of generalizations that I didn't really realize when I started playing with the Nano VNA, when I started to look into it, I thought, oh yeah, why didn't I remember that, or why didn't I know that in the first point? It forced me to learn a lot of basic things about antennas, matching feed lines. If you look at the inside of an antenna tuner, what's in there? They're just coils and capacitors. What do they do and how do they work? If you have an antenna that has an SWR of, let's say, 3:1, it's sending back a considerable voltage. So what is the antenna tuner trying to do? It takes that reflected voltage, going kind of the wrong way, right, from the antenna back to the radio. It takes that reflected voltage and with coils and capacitors reflects it right back at the antenna. In other words, the antenna might have a reflection loss, SWR coming back. What does the tuner do? It provides a reflection gain. It takes the bad energy coming back and turns around and sends it right back to the antenna. What happens when it gets to the antenna? It still has a lousy SWR and some comes back. It comes back to the antenna tuner. What does the tuner do? It reflects that right back out. So in other words, the tuner is kind of protecting the radio from seeing the bad antenna. That's the way W2DU described how an antenna tuner works, in words rather than in complex conjugate math. And I thought, oh, that's very clever. I think I can see that. None of that was obvious to me
No.
before I started to play with Nano VNAs.
Yeah, I think it's one of these things. Eventually, this sort of thing just clicks in your mind, doesn't it? And you think, yes, that makes
Yes.
sense now.
Yes.
I was much the same with the whole idea with reflected power and where does it go and what happens to it. It's yes, it's quite interesting.
Well, have fun playing with yours. And one thing I think clubs could do is buy one for the club and just send it around to different people for like 2 or 3 weeks, so you can all get some time to play with it.
Yeah.
You drop it, you buy it.
We'll probably get one of the metal case ones.
Yes, yes.
And then wrap it in bubble wrap.
Yeah.
Yes. Well, it's been fun. For you guys, it's getting kind of late now, isn't it?
Yeah.
So,
it's been good.
It's not sunset. No, it must be sunset by now.
Just about. Yeah.
Not quite. It's getting that way.
Yeah, it's just above the horizon where I am. But yeah, very informative, and thanks very much. It's been educational, very educational.
Thank you for the invitation.
Now I've got to get mine out and play with it, and now I can understand it a bit better.
Yeah, I've got to dig mine back out the box, but it's definitely coming back out.
One suggestion. Someone asked this. I said, be careful. You don't want to hook your transmitter to the VNA through to your antenna.
No.
It doesn't work like an SWR meter that we burn it out in a second. So what you can do is just disconnect your radio and attach the VNA right to your antenna or through a tuner. And you treat your VNA as if it were, a little milliwatt transmitter.
Yeah.
So it's not sending out a lot of RF energy, and you're not going to, QRM the next net. Oh, something else. Someone reminded me of this, and I said, oh, wow, I didn't know that. Someone suggested if you live close to an AM radio transmitter, 50,000 watts or something, and it's, 2 miles away, this little Nano VNA, the antenna port, is very sensitive to any RF. So what you might find is some readings are really off the scale, off the charts, like what's going on, because you're picking up some RF from a nearby, transmitter at 1 megahertz or something.
Yeah.
Or if your neighbor is a ham and he's transmitting or she's transmitting, you know, it's like, it's sensitive to any RF, including, you know, anything in your neighborhood.
I'll be pointing it in the direction of my neighbour's solar panels and see if I'm getting anything from there.
Right.
Yeah, but yeah, a lot of our AM transmitters are now defunct. But
although we still got the Asian network at Freeman's Common.
Yeah,
I think that's a few kilowatts anyway, and that I find I have to use a high pass, you know, a sort of 1600K high pass filter, otherwise it wipes out sort of non-filtered SDRs and things. Which, then I thought, because I've got the I can't remember which SDR it is now, but the Italian one, and I thought it was faulty because I just had images of the signal all over every band, and the designer actually connected and then he tuned down and said, oh yeah, sort of 826 kilohertz, you've got sort of a 59 plus 80 signal there. I was like, oh yeah, that'll be it then.
There seems to be RF everywhere now. Just the noise level on the HF bands, especially 80 and 40 meters.
Oh, yeah.
I'm surrounded by 3 what they call electric dog fences. These are wires underground, a couple inches, that are on a very low frequency, and the dogs have these collars, and as the dogs approach the edge of the antenna is a big loop, closed loop, they start to get a shock. So the dogs learn, don't cross this invisible fence line. But when I tune to the low end of 80 or 160 meters, I can hear tick, 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 the dog fence.
Yeah.
So it's generating square wave signals that are splattering everywhere. Not a lot of power.
No, but they don't need to be.
I have an electric cattle fence out the back of me, and I hear that just about everywhere. It's a constant click, click, click about once every second.
So it's charging and discharging a capacitor, I would bet.
Yeah, I think it might have a fault on it, actually.
Yeah.
But one of these days, I'm going to get an AM radio out and walk along it and find out where the clicks the loudest.
Usually you find the arcing is wherever there's a gate and there's like a hinge. Yeah. It's a metal hinge, and it's not quite making a real good contact. If you look closely, you can see little sparks. Yeah. So RF goes up into the tens of.
I suppose you get the rusty bolt effect as well with the fence where it's getting old, a bit old, and is they arcing across.
Well, if one of the cows hadn't got out of the field, I would have been all right because he wouldn't have put the electric fence up.
Well, I think it's a bit late for my dinner. Actually, I better go.
Alrighty. Time to sign off, I guess.
Well, thanks again, Barry.
Yeah, thanks very much.
Thanks very much, Barry.
Yeah.
Are you still burning the wick at both ends, Phil?
Yeah, pretty much. Yeah, still quite busy.
Phil's name to fame as part of the team that have just released some software called WF-View.
Wow.
What do you feel?
Yes, yeah. Well, it's software to control ICOM transceivers. I work with Guy Elliott, W6EL in California, who works at, his sort of proper job is at the NASA JPL, so he's quite a character. And it was amazing to tell me they've got sort of 500 hams at work there.
Wow.
Which but yeah, so that's keeping me busy because of course with the 8-hour time difference, there's not that much time that we've got that the two of us are actually awake and not busy doing, sleeping or. So usually,
right. Oh, so did you folks record this?
Yes.
Yeah.
It's still recording at the moment.
Oh, all of this jabberish. Okay. Alrighty.
So no, that's great. I just want to say thanks to anybody who's not part of LRS who has joined us tonight, and feel free to come along and keep in touch. Whenever you feel to do so. It's great to have you on board. And again, thanks to Barry for his talk. Really enjoyable, really entertaining, and educational. And again, feel free, come and join us anytime.
If you have individual questions, just write to me, K3, it's Echo Uniform India, EUI, Barry, one word, K3EUI Barry, at gmail.com. Right. So if you have questions.
I got your course line wrong then.
Yes.
You did. I wasn't going to say anything, Dave, but yeah, you did.
I wrote
EUI, EUL, that's pretty close. Yeah, that's all right.
It's my age.
I was just careful that I wouldn't mispronounce the name of your club.
Yeah, well, that's a common one. But
yeah.
It's not the easiest place name to pronounce.